Testing, can you hear me? Testing, can you hear me? Okay, my video is public now. So I'm going to be studying the discrete math book again. Last time I studied about permutation and combination. And I will continue this chapter on this stream as well. All right, so last stream, well, the last chapter I studied was this one about counting multisets. And then this stream, I will continue with the next chapter. Look at any sets in the interior Pascal's triangle and the six numbers that surround it. For example, you might look at this cell 4, 6, 5, 10, 10, 15, 20. All the six numbers surrounding our selected cell. We will divide them into two groups of three, alternating between the groups. So for this example, we have a group with 4, 10, and 15, and a second group with 5, 6, and 20. But notice 4 times 10 times 15 is 600, which is 5 times 6 times 20. Does this work no matter what center cell you pick and why? So of the six numbers surrounding our selected cell, so 4, 5, and 15, 6, 10, and 20. For Pascal's triangle, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1. So how are they doing this? 4, 6, 4, 6, 5, 10, 10, and 15, 20. Oops. 4, 6, 5, 10, 10, 15, 20. Okay, okay, I think I understand. So like 2 here, 3 here, and 2 here. Okay, let's just Do one more. 1, 7, 21, 35, 35, 21, 7, 1. Let's try these two, these three, these two. So, yeah. So it would be 10, 15, 35, 10, 15, 35. Well, it's the same. I think this is a bad example. Let's choose maybe this. Then I have 10, 15, 21, and then 5, 1, 7. 5, 1, 7. Did I choose it correctly? 4, 6, 5, 10, 10. No, I didn't. It's 10, 5, and then right below this, right below. Uh, so 10, 20, 35, 10, 20, 35, and then 5, 6, 21. 5, 6, 21. Uh, 10, 20, 35, 5, 6, 21. How are they multiplying? I don't understand. Of the six numbers surrounding our selected cell, so these six numbers, we will divide them into two groups of three, alternating between the groups. So this is groups of three, this is groups of three. So 4, 10, 15, 6, 5, 6, 20. Is it like that? Let's see. So they must be saying 10, 6, 35, then 5, 20, 21. Is it like that? Then 6, 35. Oh, it's the same. So basically, what they're saying is if we have n choose k and choose k, we pick the one above. So 5, 10, 21. That would be n minus 1, choose k times so n minus 1 choose k times it by n choose k minus 1, and then times that by choose k plus 1. So what they're saying, this should be equal to this. n plus 1 choose k. It should be equal to this times this times this, right? Let's see. N minus 1 factorial times it by n minus 1 minus k factorial and then k factorial. So just for the first one, it would be this times it by minus 1 factorial times it by k minus 1 factorial multiplied by n minus plus 1 minus k factorial and then k plus 1 factorial. And then for the other one, n minus 1 k minus 1 k minus k minus 1, right? Or minus k minus 1 factorial k minus 1 factorial. This should be plus because minus minus will make it plus. And then nk plus 1 plus k plus 1 factorial n plus 1 and k. N plus 1 factorial minus k factorial. And then is that correct? Yeah, let's rewrite this. N minus k minus 1 factorial. N minus 1, we have nk minus 1, n plus 1, and k plus 1. Minus k plus 1. N minus 1, k minus 1 for this one. And nk plus 1. N plus 1 and k. Right, so if the terms are equal, n minus 1 and n plus 1, you have k minus 1. Do we have n minus 1 minus k? Right. Let's try canceling each one out. So these exist. I want to see if each term exists in both of these. K minus 1 factorial exists in the denominator. Just k factorial does exist. K plus 1 factorial. N plus 1 minus k plus 1. That's just n minus k, right? Oh, no, wait. N plus 1 minus k minus 1. That's just n minus k. Over here, n minus 1 minus k plus 1. That's also, so this and this are same. N minus k plus 1. That would be here. n minus k minus 1, n minus k minus 1, that would be here. So the theorem is true. So this is true then. So this here is true. And the coolest thing about combinatorics is that you can often answer the same counting question dramatically different ways. When you recognize this about a particular problem, you can often generalize the question to reveal two different expressions that must represent the same quantity. The counting problem itself becomes a proof of the equality of the two expressions. This style of proof is called a combinatorial proof. Consider a 7-bit strings of Consider the set of 7-bit strings of weight 3. That is strings of zeros and ones that are 7 characters long and have exactly 3 ones. How many such strings are there? Give the answer as a single binomial coefficient. So what they're saying is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. You need like a set of these. But so by how many are there? We choose 7 factorial. 1, 2, 3, 4. 4 factorial, 3 factorial. What do they want? Give an answer as a single binomial coefficient. I don't know what they mean by this. Isn't it just 7 choose k? 7 choose k. Hold on. I thought they had like a combination. They do 7, 3, 35. Now just count those 7-bit strings of weight 3 that start with a 1. How many are there? So that means we just have to count 6-bit strings with weight 2, right? 6 with weight 2 are 15. 15. Now count just those 7-bit strings of weight 3 that start with 0, 1. How many are there? So 7 with weight 1, right? That's just 7, right? 7 weight 1. Yeah, 7. Sorry, 7 with weight 2. 21. Nope. 6 with weight 2. Or 5 with weight 2, which is 10. Now count those 7-bit strings of weight 3 that start with 001. How many are there? 7001. We are left with 4. 4 with weight 2. 6. Continue this process until you have counted all 7-bit strings of weight 3 as a sum of binomial coefficient. What is this sum? All 7-bit strings of weight 3 as a sum of binomial coefficients. What is this sum? I don't know what they're asking. Continue this process until you have counted all 7-bit strings of weight 3 as a sum of binomial coefficients. So they did 1, then they did 0, 1, then they did 0, 0, 1. So now I have to do 0, 0, 0, 1. So that's 3, 2, which is 3, 2, 2, which is 1. It's not clear what they're asking. 4, 5, 6. So we have 2, 3, 4, 5, 6. 6 is the last one, right? We end up with 35. Is this what they're asking? Have a look again at Pascal's triangle. Forget for a moment where it comes from. Just look at it as a mathematical object. What do you notice? Let's look. There are lots of patterns hidden away in the triangle, enough to fill reasonably sized book. Here are just a few of the most obvious ones. The entries on the border are all of the triangle are all one. Any entry not on the border is the sum of the two entries above it. The triangle is symmetric. The sum of all the entries on a given row is a power of 2. We would like to state this observation in a more precise way and then prove that they are correct. Now, each entry in the Pascal's triangle is in fact a binomial coefficient. The one on the very top of the triangle is 0, 0. The next row, which we will call row 1, even though it is not the most top row, consists of 1, 0, and 1, 1. Row 4 consists of all the binomial coefficient. Given this description of the elements of in Pascal's triangle, we can rewrite the above observations as follows. So n0 is 1, nn is 1, nk is the sum of the previous two. Nk is n to is equal to n and then n minus k. N0, n1, n2 all the way till nn is 2 to the power of n. How do you prove this last one? Given each, given, sorry, each of these is an example of a binomial identity, an identity involving binomial coefficient. Our goal is to establish these identities. We wish to prove that they hold for all values of n and k. These proofs can be done in many ways. One option would be to give algebraic proofs using the formula for nk. Here's how you might do that for the second identity above. When algebraic proof. Okay, I think we can use induction. Given algebraic proof that is equal to the previous two, so n minus 1, k minus 1 plus n minus 1, k. So 10 is 4 plus 6. So we do this by saying k minus 1 factorial plus n minus 1 factorial um How do we do this? So these two would remain. What about these two? I can rewrite this as n minus 1 factorial. Okay, I can rewrite this part as n minus k plus 1 times n minus k factorial. Then I can have k over here. And then, yeah, I can have k factorial here. So the k would cancel out and we would be left with k minus 1 factorial. Shouldn't it be n minus 1? Shouldn't it be n minus 1? No, no, there's a mistake on both sides. N minus 1 minus n minus k. Sorry, k minus 1. N minus 1 minus k factorial and then k factorial. So this k factorial remains somehow, and then n minus 1, we have n minus 1 minus k plus 1. The plus and minus, they cancel out. N minus k factorial and then k factorial. Then we write k here. K and k will cancel out, then we will be left with k minus 1 factorial. Then on this part, n minus 1 factorial. Let me think. I can write n minus k on top and then n minus k factorial, k factorial. Writing this on top because then this would mean n minus k would cancel out and then we would be left with n minus k minus 1 factorial. And then we can write, we can add these two. So n minus 1 factorial k plus n minus 1 factorial n minus k, n minus k factorial k factorial. And then we can take n minus 1 factorial out. Factorial k plus n minus k is n. And this is just n factorial, which proves our point. So which is equal to nck. And let me check how my stream is doing. before continuing. Because sometimes, like, I record for hours and then it doesn't get recorded. Okay, it's working fine. Explain why n choose 0 is 1 and n choose n is 1. N choose n because 0 factorial is 1. Wait. N choose 0 is like n factorial over n minus 0 factorial. 0 factorial is 1. So this is 1. N minus n. 0 factorial is 1. So this is just 1. Explain why this. We just did, right? Yeah, we just gave a proof. Prove the binomial identity. If we replace k with n minus k, we replace k with n minus k, then we have n minus k factorial. And then n minus will cancel out. The minus n minus k, this will become plus k. So this will be same as this. Now, how do we do the last one? That's the question. Uh, plus n factorial plus plus n minus 1 factorial plus n minus n. How do we prove this? I think if we want to make the denominators equal, we can like n factorial, n minus 0 factorial. We can like take this, multiply it with this, multiply it with this, multiply it with this, multiply it with this, and then all the denominators would be equal. We can multiply the denominators with each other so that they all become equal. That is what I'm thinking. No, not n minus 0. Minus 1 factorial, 1 factorial. I'm unsure about this, but I want to see what they do. Let's do a pizza proof again. We need to find a question about a pizza topping which has 2 to the power of n as the answer. How about this? If a pizza is joint offers n toppings, how many pizzas can you build using any number of toppings, from no toppings to all toppings, using each topping at most one? On one hand, the answer is 2 to the power of n. For each topping, you can say yes or no. So you have a choice. You have two choices for each topping. Wait a minute. Yeah, binary, right? Hold on. So for a bit, I have for one bit I have a total choice of 1 or 0. For so I have two options. For 2 bits, I have total choice of 1 1 0 0. I have 4 options. For 3 bits, this is going to double. So initially I had 1 and 0. I had 2 to the power of 1, just 2 options. And then for the fourth one, for the second one, initially I had 2 to the power of 1 options, just 1 and 0. Then 1 1 0 0, I had 2 to the power of 2 options, 4 options, and then it gets doubled. So 2 to the power of 3 options, 8. Then for this one, I have to have 2 to the power of 4 options, and so on. K length bit strings gives 2 to the power of k options, right? Now, but for combination, wait, two for 4 length bit strings, I have 2 to the power of 4 combination. And what they're saying, 4 choose 0, 4 choose 1, 4 choose 2 should be equal to the power of 4, right? So 4 choose 0 is a 4-bit string with weight 0. 4 to the power of 1 is a 4-bit string with weight 1. 4-bit string with weight 2. 4-bit string with weight 3. 4-bit string with weight 4. 4-bit string with weight 3. Let me think about that. Okay, I have no clue. Wait. Divide the possible pizzas into disjoint group. The pizzas with no toppings, the pizzas with 1 toppings, the pizzas with 2 toppings. If you want no toppings, then there is only one pizza. But would it be better to think that number as n choose n since we choose 0 of n topping, n choose 0 since we choose 0 of n toppings? How many pizzas have one topping? We need one of n toppings. So n choose 1, we have n choose 0, n choose 1, n choose 2, n choose n. The total number of possible pizzas will be the sum of these, which is exactly the left-hand side of the identity we are trying to prove. Again, we could have proved the identity using subset bit strings or lattice patterns. I'm trying to use bit strings. How do you prove it? And just write 0, or I will just write 1. And then this repeats with zeros. I can just write it. So this is n choose 0. And then we have n choose 1. Um, which would be 4. Oh, I think I understand. So n choose 0, all the possible, pick all the possible options with which has no ones, and choose 4 is the total number of bit strings with weight 1. 4 choose 2 is the total number of options, total number of bit strings with weight 2. 4 choose 3 is the total number of bit strings with weight 3. 4 choose 4 is the total number of bit strings with weight 4. And that covers all of them, right? That covers all of them, which is like 2 to the power of 4 options in total. Yeah, I think that's one way to prove it. I wonder if there's like an algebraic proof. Expand the binomial x plus y to the power of n. Let x is equal to 1, y is equal to 1. We get, oh, we can do this. Of course, this simplifies to the power of n. I could have just used the binomial coefficient. The explanatory proofs given in the above examples are typically called combinatorial proofs. In general, to give a combinatorial proof for a binomial identity, say A is equal to B, you do the following. Find a counting problem you will be able to answer in two ways. Explain why one answer of the counting problem is A. Explain why the other answer to the counting problem is B. Since both A and B are the answers to the same question, we have A is equal to B. The tricky thing is coming up with the questions. This is not always obvious, but it gets easier to the more it gets easier, the more counting problems you solve. You will start to recognize types of uh, answers to as the answers to types of questions. More often, what will happen is that you will be solving a counting problem and happen to think up of two different ways of finding the answer. Now you have a binomial identity. The proof is right there. The proof is the problem you just solved together with your two solutions. For example, consider this counting question. How many 10-letter words use exactly 4 A's, 3 B's, 2 C's, and 1 D? 4, 1, 2, 3, 1, 2, and 1. There are 10 letters in total, right? Take 10 factorial divided by 4 factorial divided by 3 factorial divided by 2 factorial divided by 1 factorial. Let's try to solve this problem. You have 10 spots for letters to go. 4 of these needs to be A. We can pick the four A spots in 10 to the factor, then choose four ways. Now, where can we put the B's? Well, there are only six spots left. We need to pick three of them. This can be done in six choose three ways. Two C's need to go in two of the three remaining spots. So we choose two ways of doing that. This leaves just one spot of the D, but we can write that one choice as one choose one. Thus the answer is this. Why stop there? We can find the answer another way too. First, let's decide where to put the one D. We have 10 spots and we need to choose one of them. So this can be done in 10 choose one ways. Next, we choose one of the 9 choose two ways to place the two C's. Now, we now have 7 spots left. 3 of them need to be filled with B's. There are 7 choose 3 ways to do this. Finally, the A's can be placed in 4 choose 4 ways. So another answer to this question is this times this times this times this. This gives us the binomial identity. Here, a couple more binomial identities with the combinatorial proofs. Prove the identity 1 n plus 2 n minus 1 plus 3 n minus 2 is equal to this. Okay, let me think. You're doing 1, 2, 3. We use the binomial coefficient. To give a combinatorial proof, we need to think up a question we can answer in two ways. One way needs to give the left hand side of the identity, the other way needs to be the right hand side of the identity. Our clue to what question to ask comes from the right hand side. 2 plus n plus 2, choose 3, counts the number of ways to select 3 items from a group of 2 plus n plus 2 things. Let's name those things 1, 2, 3, all the way till n plus 2. In other words, we want to find three element subsets of those numbers. Since order should not matter, subsets are exactly the right thing to think about. We will have a bit we will have to be a bit clever to explain why the left hand side also gives the number of these subsets. Here is the pro. Consider the question, how many three element subsets are there of the set 1, 2, 3 all the way till n plus 2? We answer this in two ways. We must select three elements from the collection of n plus 2 elements. This can be done in n plus 2 choose 3 ways. Break this problem up into cases by what the middle number in the subset is. Say each subset is A, B, C written in increasing order. We count the number of subsets for each distinct value of P. Smallest possible value of p is 2, the largest is n plus 1. When b is equal to 2, there are n subsets, 1 times n subsets, one choice for A and n choices for C. When B is equal to 3, there are 2 times n minus 1 subsets, 2 choices for A and n minus 1 choices for C. When B is equal to 4, there are 3 times n minus 2 subsets, 3 choices for A and n minus 2 choices for C. And so on. Okay, I understood. Prove the binomial identity. Square, 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 square. I see 2n, choose 2. Okay, let's see. We will give two different proofs of this fact. The first will be very similar to the previous example. The second proof is a little slickier using lattice patterns. To prove how, consider the question, how many pieces can you make using n toppings? And there are 2 to the power of n toppings to choose from. There are 2 n toppings. There are 2 n toppings from which you must choose n. This can be done in 2 n choose n ways. Divide the toppings into 2 groups of n toppings. Any choice of n toppings must include some number from the first group and some number from the second group. Consider each possible number of meat toppings separately. 0 meat, and choose 0 and choose n, since you need 0 of the n meats and n of the n veggies. 1 meat, and choose 1 and n choose n minus 1, since you need 1 of n meat and n minus 1 of n veggies. 2 meats, and choose 2 and n choose 2 minus n minus 2, choose 2 meats and the remaining n minus 2 toppings from the n veggies. The last case is n meats, which can be done in n choose n and n choose 0. But can't we do this algebraically? Like, if we, let's try to do it algebraically. So n choose k is this, right? And then n choose n minus k would be something like this. This is what they're doing, right? If we multiply them, sorry, wait. No, I don't think this would work. Let's see what else is there. Which of the following describe the overall strategy for combinatorial proofs? Ask 2 counting questions that both can be answered in the same way and answer the other questions. Ask a question that can be answered in 2 ways. Yes. Right, how much time do I have? I might end my stream if I don't have a lot of time. Okay, I think I will end the stream here then. And yeah, I'll see you guys next time. I'll continue with the next topic in the next stream. It seems to be about probability. Anyways, see you guys next time then. Bye.